Hello, hello, hello. This is Coach Ikram, and welcome to the first video for the Thermochemistry unit. This video is going to talk about the basics of thermochem, including the concepts of endothermic and exothermic, as well as energy diagrams. So let's go ahead and start with looking at the objectives for the unit as a whole, so we can kind of see where we're going from here. We're going to understand energy in its forms. We're going to understand the law of conservation of energy and the process of heat transfer. We're going to perform calculations that involve heat, mass, temperature change, and specific heat. We're going to use calorimetry to calculate the heat of a chemical process. And we're going to use thermochemical equations to calculate energy changes that occur in chemical reactions and classify those reactions as endothermic or exothermic. All right, so this unit, or at least the beginning of it, is a lot of basic conceptual ideas for thermochem. And these are really important, especially for this unit. You need to understand the fundamentals and the basics before you can go on and do more complex and complicated equations and calculations. So make sure you really take the time to learn these terms and learn the kind of basic vocabulary, because that's going to help you in the long run. So in thermochemistry, we're going to look at how heat flows, oops, sorry, I'm a little off my calibration, between a system and its surroundings. And these two terms you do need to understand. The system is the reaction or the process that you're actually investigating, and the surroundings is going to be everything else. And primarily, when we're looking at what's going on, we're going to be looking at the system. In a thermochemical process, heat flow is given from the point of view of the system. So just to reiterate what I said in the last slide, the system is kind of the focal point, or the substances that actually start that process. So for example, if we're looking at ice, when ice takes in energy, again, the calibration, sorry, it's adding heat. So if you think about it, you've got ice, you've got a solid, you take on heat, you leave it out in the sun, you leave it out on the counter, takes on heat, and then it melts and becomes liquid water. That is an endothermic process, because that ice, from the perspective of the ice, is gaining the energy. If you think about it in the opposite, the water, if it wants to freeze, you have to release the energy. So you've got water on an ice cube tray. The heat energy inside that water is transferred to the surroundings, and it loses that heat, and then it becomes solid ice. And that's going to be an exothermic process. So remember, just to kind of reiterate from what we've done in the past units, endothermic gains energy, exothermic releases energy. The law of conservation of energy states that energy is neither created nor destroyed, but it can be transferred from one form to another. In this unit, we're going to focus on heat energy transferring or flowing between objects and the kinetic and potential states. So we're going to focus on heat changes that occur during a chemical reaction or change in state. It's really good to look at that visually. And these two visuals, you're going to, especially this first one here, you're going to see quite often. This is an energy diagram, and we're going to talk about it in a few slides. But this is going to show the energy difference between the reactants and the products. And how that graph is oriented is actually going to tell us if the reaction is endothermic or exothermic, because you're going to be looking at that potential energy between those two. This diagram over here, let me move this real quick for you. This diagram, this is a diagram that kind of shows you the different states of matter. It can be anything, and water being a very common example. You've got your liquid, your solid, and your gas here. And in between, you've got the names of the processes to go between those different states of matter. So for example, if you go from solid to a liquid, you are either melting or undergoing fusion. If you go in the reverse, from a liquid to a solid, you are freezing. Most of the terms you're probably actually fairly familiar with: vaporization, condensation, etc. But you might not know sublimation, you might not know deposition. So take a look at those terms if you're not familiar with them. Write that down. That's a really good reference. You're going to use those terms a lot, especially when we get into phase change diagrams late in this unit. That's going to be video 6. So you will need to know those terms if you're not already fairly familiar with them. Oh, there we go. Energy. The definition of energy is the capacity for doing work or producing heat. Kinetic energy is the energy of motion, and that should make some sense. That kind of is a throwback to when we really talked about kinetic energy with gas laws. Talked about, increasing the temperature increases the kinetic energy of molecules. When energy is stored in the bonds of a substance, it's going to be called, oh, there's a way to pull this word up. There we go. Potential energy. So kinetic energy, motion, potential energy is when it's stored in the bonds of the substance. So for example, when a car is burning gasoline, the energy that's stored in those chemical bonds, it's potential. It's then released to do work. And that's how your car runs. heat is going to be notated with a Q. Oops, sorry, my calibration is really driving me crazy here. Heat's going to be notated with a Q, and by definition, heat is the energy that transfers from one object to another because of a temperature difference between them. The SI unit for it is going to be joules, and heat, it's worth noting, always flows from a warm object to a cold object. So the example I always like to think about with that is a cold pack. If you put, or a cold pack or an ice pack, if you've got an injured knee and you put an ice pack on your knee starts to feel, from your perspective, cold. That's not because the ice pack is transferring cold to your knee. That is because your knee is transferring heat to the cold pack. This is why the cold pack eventually becomes useless and warm, and your knee is cold and therefore heals, etc., etc. So heat always goes from the warm object to the cold object. Heat as an energy can be measured in what we call calories, not to be confused with calories with a capital C. In food, when you talk about calories on the back of your nutrition label, that's actually kilocalories, which is 1,000 calories. But we notate it in this with the same word, we just use the capital C. And it's also worth noting, heat is not the same thing as temperature. Okay, heat is not the same thing as temperature. Those are not equivalents. Enthalpy is the internal energy content of a system plus the product of the volume and pressure of that system at any given temperature. We can't measure it directly, but we can measure the energy lost or gained by the system when the reaction takes place. These values are called the change in enthalpy, and that's notated with this delta H right here. It's very important. And it's also known as the heat of the reaction. So change in H is going to be equal to Q. We've done problems and with Q when we do this equation. You remember from the very beginning of the year. We are going to relook at that in the next video. But this Q value, remember, if it was negative, positive, it told you if something was exothermic or endothermic. The same is true of the change in enthalpy. So change in enthalpy is going to be equal to your Q. And when you calculate it, which we're going to do later on, it's equal to the enthalpy of your products minus the enthalpy of your reactants. And that gives you the overall change in enthalpy of the whole reaction. So there's different types, 4 forms. I'll move this down for you. Oh, maybe. 4 forms of energy. Okay, I'm going to let that go. 4 forms of energy. The first one is kinetic energy. It is due to the motion of a substance molecules. Okay, some examples of it: light, heat, sound, mechanical motion. Temperature, by definition, is the average kinetic energy of a substance. Remember, we said in the last few slides, temperature is not heat. Temperature is average kinetic energy, which should be very familiar because of our gas law unit. Tie that in. Make sure, remember, it all comes back around. Potential energy, like we said before, is the stored energy due to the position or arrangement. So a stretched rubber band, a chemical bond, and a nuclear bond. And so we got this little visual of this guy about to roll this thing down the hill right here. That's got a lot of potential energy where it sits. Thermal energy is the total of the kinetic and potential energies of a substance caused by the composition of the substance and motion of its atoms, ions, and molecules. So it's basically taking kinetic, sorry, I'll just rewrite that, kinetic and potential. Chemical energy is the potential energy that's stored in the bonds between atoms of a substance. So chemical energy is a type of potential energy. Every reaction involves a change in chemical potential energy. Reactants transform into products which either have more or less potential energy than the reactants. And this is how we come to the definition of exothermic and endothermic. If you have exothermic, again, we've talked about this, the system is going to lose heat to the surroundings. Therefore, the heat's going to flow out of the system, and the heat's going to be expressed on the product side of a reaction. So when you write it, heat is going to be one of your products. It's going to have a negative change in H, and therefore also a negative Q, which we have covered before. That should be familiar. If you have something that's endothermic, the system is going to gain heat from the surroundings. The heat's going to flow into the system, and the heat's going to be expressed as a reactant on the left-hand side of the reaction. It's going to have a positive change in H, and therefore a positive Q value for heat. If we look at that visually, exothermic, and again, this is coming back to that energy diagram that we talked about before. Looking at this energy diagram, right here is your energy level of your reactants. It undergoes the reaction. It has to overcome the activation energy for the reaction to actually take place. And then it releases all the energy until you have the final energy or potential energy of your products. If you notice and you look at this, the energy of the reactants is up here. The energy of the products is down here. Therefore, the products have less energy. Therefore, energy was released. So that's going to be exothermic. And if we show you this down here, potential energy of the system went down, and the thermal energy of the surroundings went up. And so it's going to feel hot, which is why when you put your hand on the side of a beaker that's in an exothermic reaction, it feels warm to the touch. On the contrary, if we look at endothermic reactions, you've got your reactants with their potential energy down here, your products with their potential energy up here. And so overcoming that activation energy, when we get to our final result here, you notice that our overall potential energy of our reaction was absorbed. We have more potential energy than what we started with. So we have a positive change in H, and we're endothermic. So potential energy of a system went up. Thermal energy of the surroundings goes down, because remember, they went into the system. That energy went into your system. And so it's going to feel cold to the touch. So looking at these here, go ahead and pause your video and see if you can, based on your knowledge, tell if these are endo or exothermic. So go ahead and pause it. All right, so let's look at these. Hopefully you jotted down some answers. Evaporation of alcohol is going to be endothermic. Water cooling is going to be exothermic. Leaves burning is going to be exothermic. Ice melting is going to be endothermic. Boiling water is going to be endothermic. And freezing water is going to be exothermic. The graph shows the energy change during the reaction. So here's what we were kind of looking at. We've got A plus B yields C. Okay, here's our reactants, A plus B at this particular potential energy. We overcome our activation energy, and we're left with C as our product. The products, it says, have more or less potential energy than the reactants. So my products have more potential energy than my reactants. Therefore, my reaction had to gain energy to get to that point, so it's going to be endothermic. On the graph below, draw the reaction progress of an exothermic reaction. So we're talking about something that's exothermic. Remember, it had to lose energy. So I'm going to start with my reactants here, overcome my activation energy. And remember, I've got to fall to a lower potential energy than what I started with. So this is my reactants, and this is my products. This is my change in H. And because it's exothermic, remember, change in H is going to be negative. So is Q. Just to tie it all together for you. So looking at this particular drawing here, the energy of the reactants, the total potential energy of all the reactants in the reaction. So our change in H for the reactants, if we look on the graph, is at 150 kilocalories per mole right here. The energy of the products, looking down where the products are, is at 50. Overall, the difference in that potential energy, calculating enthalpy, products minus reactants. So products is 50 minus 150. So my change is going to be negative 100 kilocalories per mole. Is that endothermic or exothermic? That is exothermic, because my change in H is a negative number. And also, visually, my products have a lower potential energy than my reactants. Therefore, they lost energy, and it's exothermic. Looking at a second one, the enthalpy change in my reactants is 100. Enthalpy change in my products, look at the graph, 300. If I take the overall change in enthalpy, it's going to be products minus reactants, so 300 minus 100, that's a positive 200 kilojoules. Which letter on the graph represents the change of H in the reaction? It's the difference between your products and your reactants, so it's going to be right here, and that's going to be C. And then this is going to be an endothermic reaction. All right, that is where we're going to stop, and we're going to pick up with calories, joules, and energy units in video number 2. So go ahead and rewatch the video if you have more questions. Make sure you took good notes. Make sure you write down any questions that you have, and we will go over them in class. Thanks, and have a great day.